It'll be fine.
Pessoal, bom dia a todos. Bom dia a todos, bem-vindos a mais um colóquio aqui do Instituto de Física de São Carlos. Agora a gente vai retomar o programa de maneira remota, porque por causa da pandemia. Então a gente hoje tem o prazer de receber o Phil Bucksbaum para abrir esse programa. Tá? Então vai ser, em princípio é um programa que vai ser um pouco irregular, então ele não vai ser semanal. Tá? Então hoje a gente tem uma palestra do Phil Bucksbaum e daqui a 15 dias a gente já tem outra palestra agendada, tá? Do Salé, também de Stanford. A gente vai anunciar na semana que vem, na sexta que vem, para vocês terem todas as informações aí. Tá? Então eu sou o Eric e organizo esse colóquio juntamente com o Gregório. Então eu vou pedir para vocês que quem tiver dúvida, né, durante o colóquio, que encaminhe essas dúvidas pelo chat do YouTube, tá? E ao final da palestra eu vou retransmitir as perguntas da melhor maneira possível para o Phil, para ele poder responder, e a gente faz a sessão de perguntas e respostas, tá? Se algum estudante quiser perguntar em português, não tem problema, eu traduzo da melhor maneira possível para o inglês, tá? Então, para não ter um problema de barreira de linguagem. Tá, então agora eu vou passar a palavra para o Vanderlei poder apresentar o Phil, tá? Bom, a gente pode dar início ao programa. Vanderlei, please.
Okay, Eric. Hello, Phil. I will do this introduction very briefly, and I will do in English, right? Because from now on we go to the official language of the colloquium. Okay. So it is a pleasure for us to have here Professor Bucksbaum. Professor Philip Bucksbaum is professor at Stanford University, where he is presently conducting his research in the so-called Stanford Pulse Institute. Bucksbaum graduated from Harvard in 1975 and received his PhD in 1980 from Berkeley. Work on a very important topic of atomic physics called atomic parity violation experiments. And in Berkeley, he works under the guidance of Professor Eugene Cummings. In 1981, he joined the Bell Laboratories, where he pursued new applications of ultrafast coherent radiation from terahertz to vacuum ultraviolet, including time-resolved VUV ARPS, and strong field laser atom interaction. In 1990, he joined the University of Michigan, where he stayed for 16 years. He was a founding director of the National Science Foundation Physics Frontiers Center in Ann Arbor, Michigan, where he pioneered research in ultrafast laser and control of coherent process. He also launched the first experiments in ultrafast X-ray science at the Advanced Photon Source at the Argonne National Lab. Since 2006, Professor Bucksbaum joined the Stanford University to develop research using world's first-class hard X-ray free electron laser. Professor Bucksbaum is fellow of the main institutions in the United States and around the world. He has received many, many prizes. I'm not going to list all. And he is the president of the American Physics Society. Well, besides being a wonderful and very well recognized scientist, Bucksbaum is a very nice person. And he has a few friends in Brazil, including myself and Professor Marcassa here in your institute. And I am very happy he accepted the invitation to give this first colloquium of the semester for us. And I hope we all enjoy. And please, Bucksbaum, be welcome to our institute, even in a virtual way. And I hope in the coming future, we all gonna pass all this pandemic situation and we can have you in person here to tell us much more about your science and your present status as president of the largest physics society in the world. Thank you, and now you can start your colloquium.
Well, thanks very much, Vanderlei. I really appreciate the invitation to come to San Carlos, even only virtually. It's a great institute, and I'm really excited to tell you a little bit about the science that I do. But as Vanderlei mentioned, I'm currently president of the American Physical Society, and I made a vow that this year, whenever I give a colloquium, I will at least say a little bit about APS. For those of you who don't already know who we are, the American Physical Society has 55,000 physicists in it, of course, predominantly in the United States, but also worldwide. You probably know about the APS because we publish the Physical Review with about 20,000 articles annually. But we also have dozens of research meetings and a lot of programs to support young scientists, women, ideas about careers. And then very importantly these days, I think, the APS speaks out on behalf of the interests of physicists in the United States capital, Washington, and also internationally. So if you're at all interested in that, I invite you to join us and become a member, attend a meeting, publish a paper, participate, and help us advocate for science. And you can do that by taking a photograph of this code, and this will take you to aps.org. So that's the end of the advertisement, but really the APS is a wonderful organization. But let's spend our time talking about physics. So what do I do? Well, I study the motion of molecules on their natural timescale, and not only the atoms in them, but also the electrons in them. And the way we do this is like much gas phase experimental research in AMO. We have a collection of our target gas, atoms or molecules. We hit it with a laser. In this case, we want to know what happens when the excitation is particularly strong. And then we just look to see what happens. So let me show you, just by way of introduction, a few of the things that we see. First of all, electrons come streaming out of atoms and molecules when a focused high-intensity ultrafast laser hits them. And the electrons come out in an intricate pattern that tells us about the structure and the dynamics going on inside the atom. Also, not just one electron comes out, but sometimes several, and when that happens, you get a Coulomb explosion. So then we also get to look at the ions. So this is a picture, it's just some raw data of the Coulomb explosion of water molecules that were multiply ionized by the laser. And the color code there is pretty obvious. You can see where the hydrogens went, and you can see where the oxygen went. Now, because that motion is really fast, we like to make movies. We do this using a stroboscopic method. And this is the famous pump probe spectroscopy that really occupies much of the methodology of the kinds of physics that we do. To do pump probe, you need to have an excitation source, just like the one I showed you schematically on the previous slide, but also you need to have a probe and a known time delay between them. So for example, if the probe is an X-ray laser, then the X-ray photons scatter into a pattern that also tells you about the structure and how the structure changes with time. So on the right there, you see the time advancing in fractions of a picosecond as I change the delay between the pump and the probe. So that is, generically a very common method that we use. And then finally, one of the things we like to do in high intensity laser atom physics is go to the highest intensities possible. So what is the highest intensity possible? Well, it's the intensity where the vacuum becomes unstable and breaks down into matter-antimatter pairs, and we study that as well. So that's an extremely broad range of different intensities, but it's all done with lasers, it's all done with short pulse lasers, and it's all analyzing the structure of things at the quantum scale. So let's now kind of unwrap that and look at what's going on inside an atom when it's excited with a laser pulse. First of all, atoms, as I'm sure you all probably know, have a nuclear charge that holds the electrons in a potential well. And so this is a potential well of a generic atom. I think this one happened to be a hydrogen atom. And you can see that the electrons in a hydrogen atom, the single electron, occupies a ground state, which is really just a standing wave in a particular energy of the potential well. In an excited state, it just occupies a different standing wave. And neither one of those two charge distributions is moving at all. So that's not where the motion happens. The motion happens when you excite the atom in such a way that it occupies two of those states at the same time. Of course, this is possible using the rules of quantum mechanics, and that creates a superposition, and because the energies are different, that induces motion. And that's the kind of motion that we're always looking at in atomic and molecular physics. The wave packet oscillates, and the oscillation frequency tells you about the energy differences, and the motion tells you that the electron is actually occupying a different place at different times. Okay? So how do we tell that? You know, that's the excitation part. What about the probe? Well, to see the probe, how the probe works, let me explain something that is on its surface very simple. If the electron is stored at a particular depth in this potential well, in order to see the electron, I have to tip the well and get the electron to flow out. But of course, the obvious way to do that is just impose an external field, a static field, for example. And if the field has the correct size, the state that the atom is in will no longer be a bound state, because you see there's a little leak in the potential well, and it can leak out. And when it leaks out, the electron comes out and can hit my detector. So if I have a lot of states that are all occupied in a superposition, and I slowly start tipping the potential by ramping up a field, every time I get to one of those states that makes up the superposition, it comes popping out. And I can see what the makeup is of the superposition state. Now that's not enough to show me the motion except in an indirect way. In order to get the motion directly, we have to provide another trick, and that's a very common one used in science. It's interference. We can create some superposition, say this is a cesium atom, and I'm going to show you some data. So this is not just generic now. It's already in a single excited state when I excite it, and I excite it to the superposition state with a shaped pulse. And then in order to see the motion, I have to come in later using this pump probe method, as I mentioned, with a reference pulse, which creates its own wave packet that superposes again. And the interference between the reference and the shaped pulse tells me what the shape of the wave packet is at the time of the interference. So let's show you how that works. As I vary this time delay, you can create you get a different pattern of occupation based on the interference for every time delay. You can put them all together into a molecular movie. So this really is a movie. This is a movie of the electron inside an atom. This is nearly 20 years old now, so this is something we've been doing for a long time. This axis and this axis are spatial axes that show you where the electron density is relative to the nucleus here. And this axis is the amount of the electron, and the color is the phase of the electron wave packet at that time. You can see the wave packet moving back and forth in a very complicated way. And this is what really does happen in atoms that are excited. Well, that's actually done in a fairly weak field regime. But the physics stays the same as I turn the field up and up and up. And some of the strongest fields I can make are actually made by not an external static field, but a focused laser field. The focused laser field, of course, oscillates, but at its peak, it can have a magnitude that's so large that can actually tip the electron out of its ground state. So even the ground state of hydrogen can be ionized just by field ionization in a strong laser field. And I made a little simulation movie to show what that looks like in hydrogen. Here it is. Okay. So here is the hydrogen 1s state, and here's the laser field turning on, and then it'll turn off and go on the other direction. And you can see that at its very peak, a little bit of electron starts to leak out of the ground state of hydrogen, just part of the probability amplitude. And now the field reverses and it starts getting pulled back. And as it gets pulled back, electrons get pulled off in the other direction, but look at the ripples. That's the interference between electrons that are leaving for the first time and those, or not electrons, but pieces of an electron and part of a probability amplitude that's coming back. Okay? Now, we can use a very similar apparatus to see that kind of information. Here's now the focused laser focused into the atoms. And now, instead of a ramped field, it's just the laser, but we again collect the electrons on an imaging detector now and look at the image. So what I'm going to show you next is what the image looks like on this detector. And here's what it looks like. This happens to be for a krypton atom, where one electron was field ionized using the method that I just described. And you can see that the pattern is extremely, extremely complex. Perhaps the thing that first catches your eye is a series of concentric rings that seem to be getting closer and closer together. I'll just draw lines so that you can guide the eye can see. Well, of course, this is in the velocity space or the momentum space of the electrons in this planar, in these two dimensions defined by the plane of the detector. If I convert this transverse momentum into energy, then I see actually these rings aren't changing their spacing. In energy, they're exactly evenly spaced, and the spacing is 1 photon. So what we're seeing here is a kind of a crossover between the classical field ionization of an electron and the quantum mechanical absorption of photons. In fact, if I just start from the ground state and start adding up photons, I can see how many photons net, that is, accounting for the number absorbed and the number emitted, but the net number of photons were absorbed in order to produce the energy to create these electrons. Now, this makes it look like it's just a simple multi-photon process, but I can assure you that it isn't. And one of the most easy ways to see that is to look at other parts of this pattern, which we're going to do here. Now, I hope I can see very well because it didn't have to be transmitted all the way across the 2 continents, but I hope that you can also see in this movie the green trajectories. This shows the path that an electron will take simply because it's being driven by the laser field after it's ionized. So you see, depending on when it's ionized, you can have a really different trajectory. And sometimes, in fact, pretty often, an electron that's emitted will come back and crash back into the atom at a later time. Now, when that happens, again, you get an interference pattern. The outgoing electrons are quantum mechanical waves that are spherical like this, but the returning electrons have a much larger radius of curvature. In fact, they're pretty much like plane waves returning, and they end up at the same place on your detector. That means that they quantum mechanically interfere. And what does the interference pattern look like? Well, let's take a look. You see that the maxima and minima have these spider leg shapes, and you can also see those directly in the data. Okay? So that's another important feature telling you now directly about the dynamics of electron motion. Now, actually, these returning electrons, they do quite a lot. Let's take another look. We're going to now zoom out so that we can see even higher momentum electrons. So here's a zoomed out picture. I switched atoms on you. This happens to be argon, but if you're a true atomic physicist, you'll know that the atom itself doesn't matter. It's the physics inside the atom that matters, and it's quite universal. Well, you can see that outside this pattern that you were seeing before, there's a new pattern, this extra stuff. These correspond to rescattering events, where an electron that was ionized near the peak of the oscillating electric field has a trajectory that takes it away from the atom and then back in, crashing back into the atom. And when it crashes back in, it can elastically scatter away. And those rescattering rings should follow these red circles that I've drawn here, just the classical kinematics. And you can see that the rings that we're observing really do observe that pattern. So this is actually a way of now doing very, very fast, ultra-fast science, because the dispersion in these trajectories is produced by very, very tiny differences in the ionization time. In fact, the three trajectories that form these rescattering rings were released about 20 attoseconds apart. That's 20,000ths of a single femtosecond. Typically, the oscillation period here is a couple of femtoseconds, and so that gives you the scale. And when they return separated by about 400 attoseconds, with an enormous range of electron momentum. Now, those returning electrons, the same ones, and here I'm showing their trajectories again, they don't necessarily just rescatter. They can also recombine. And when they recombine, energy conservation says the energy has to go somewhere. It goes into a photon, a burst of vacuum ultraviolet photons, one for every recombining electron in the gas. And those photons, because of phase matching, go exactly the same direction as the laser beam. So this is like a narrow pencil beam of coherent vacuum ultraviolet radiation. And of course, its energy is determined by the recollision energy of the returning electrons, which you can see is itself quite dispersed. Now there's a recollision every half cycle, and the superposition of all of those recollisions on your detector make a series of peaks in the vacuum ultraviolet spectrum sitting right on top of odd harmonics of the drive laser. So we get this beautiful vacuum ultraviolet spectrum. A lot of people just use this as a vacuum ultraviolet light source. We, of course, we're AMO physicists. We use it to study the source. We use it to study the structure of whatever it was producing the harmonics. So for example, in the case of a nitrogen molecule, which is a very good molecule to make these harmonics, depending on the orientation of the molecule in this ensemble, if we can actually adjust that, you get a different spectrum, and the changes in the spectrum tell you about the electronic structure in this molecule when it's driven by a strong field. So there's a lot of physics that's come out of studying that sort of thing. Furthermore, one very interesting thing that happens when molecules are driven in this regime where they produce harmonics is that you don't just get one electron that comes out. In fact, there seems to be an enhancement mechanism in a strong field so that once one electron comes out, other electrons follow. In fact, this is an active field of research, all of the things that contribute to that enhancement. But the enhancement happens, and so that means that not only do you get much more highly structured information in the above threshold ionization spectrum, this now happens to be for water, but you also get Coulomb explosions. Once you remove more than 2 electrons from a molecule, that destabilizes it and the different charged parts push away from each other. And that is another real avenue to learning about dynamics at this sub-femtosecond scale that's going on inside atoms and molecules that are driven by strong fields. Okay, so I've talked about these lasers as though you just buy them off the shelf. And actually, that's true. But I've been in this business a long time, and you didn't always buy them off the shelf. And furthermore, the ones that are really at the state of the art, you still don't. So I should at least spend a couple of minutes telling you a little bit about how this light is produced. And of course, it's a particularly exciting topic because about a year and a half ago, it received a Nobel Prize for the invention of chirped pulse amplification. So let me just explain just briefly what that is. The problem in strong field physics that we always face is that we're trying to produce lasers that, when they're focused, get to intensities that are so high that no matter can remain stable. But how do you make a laser? You have to use matter. As you know, lasers are produced by stimulated emission. You need some material that has energy levels that you can excite. Well, once the laser gets intense enough, it won't just experience gain in an amplifying medium, it will actually destroy the medium. And so that placed an upper limit that we all faced in the mid-1980s in how we could use lasers to study high-intensity science. And then this team of Donna Strickland, a grad student, and Gerard Moreau came up with the trick that immediately now we all use. And the trick is that the short light pulse that you'd like to amplify consists of a lot of colors just from Fourier's theorem. Short pulses have to have a rainbow of colors. And so we can use a dispersion device like gratings. And actually, a lot of this work, a lot of this technology was invented by people who are postdocs and graduate students. And here, one really has to credit Oscar Martinez for having devised some of the important stuff that goes in here when he was a postdoc. The chirped pulse has a much lower intensity. It can go through power amplifiers without destroying them until its peak intensity gets just to the destruction point. But it's still a very long pulse. And another dispersive device can put it back together and make a short pulse whose peak field now is so high that you could never get additional gain by putting it through a power amplifier. It would destroy the power amplifier. So this is a way of getting factors of up to 10,000 increase in the power of a laser. And this immediately can be seen on a chart that, because of Gerard Moreau's importance to this field, we call a Moreau chart, of what is the most powerful laser that you can make as a function of year, kind of Moore's law. And you can see once CPA was invented, we took off on a new advancing curve. And we're currently, right now, in this area of a few petawatts for a laser. Now, something that's not as well known is that the reason Donna was doing this for her thesis was she wanted to study just the same physics that I've been talking about. And she did with her colleague, fellow graduate student, Steve Oxt. Here they are with, this is the very first thing that CPA was ever used for back in the 80s. They looked at this process, field ionization, not just from hydrogen, but from more highly stripped ions as it takes a stronger and stronger field. And they wanted to see if the ionization threshold followed this simple idea that it's just the depression of the Coulomb potential. And this is their data. They saw that that was in fact true. So now we have petawatt lasers. And I should orient you a little bit about what is a petawatt, how much is a petawatt. It is actually not enough, but I can explain a little bit more about what a petawatt laser is. Typically, petawatt lasers are run in the near infrared. So choose, for example, 800 nanometers, where titanium sapphire lasers work that we use in our laboratory. And a petawatt laser, to get to a petawatt, you need 100 joules in 100 femtoseconds. That equals a petawatt. And you need to focus it as tightly as you can to get into an intense field regime. Well, the most tight focus that's ever been made is around 10 to the 21 watts per square centimeter. And so we can look at what that intensity is and what that energy is and try to compare it to things in our ordinary life. The total energy, 100 joules, is about the kinetic energy in a pitched baseball, or if you don't happen to be a fan of American baseball, it's also the number of energy calories in a potato, or about 10 times the energy in one electron bunch coming from the SLAC linear accelerator, where I do a lot of my research now. The peak power, 1 petawatt, is about 100 times the world's power consumption rate. So, of course, since it's made in the world, it can't possibly be on for very long, and that's why having it be only 100 femtoseconds is actually critical to getting to these peak powers. Now, if we focus it, the focused intensity is greater than the intensity, the radiant intensity at the center of the sun. And in fact, the RMS electric field, the field that's available for field ionization, is 100 trillion volts per meter. So let's just put that on a scale of what kinds of intensities we might want to do in physics. So here again, for reference, is the Strickland-Oxt original paper on strong field ionization. We would really like to get intensities high enough to get to the Schwinger critical field. What's the Schwinger critical field? That's the field where the vacuum itself breaks down. The vacuum, as we all know, because we're all physicists, the vacuum is not an empty place. It has little electron-positron pairs and also other matter-antimatter pairs going around in it all the time, but not lasting very long. They can only have a lifetime that's about given by the uncertainty principle, h bar over 2mc squared. Now, during that time, the electron and positron can move apart, but the farthest they can move apart is about 2 times the Compton wavelength, and we can do work on them with our laser during that time. If we do enough work to overcome their rest mass, then the electron and positron will pop out of the vacuum. So that's a really simple back of the envelope calculation that shows you that we need that intensity in order to make the vacuum unstable. And that means we need a critical field of about 10 to the 16 volts per centimeter. Let's take a look at what we can do these days. Well, at around 10 to the 20 watts per square centimeter, you can fully strip argon. And around 10 to the 22 watts per square centimeter, that's where the most tightly focused lasers can get. That's the focused petawatt laser in 2020. At 10 to the 25, which is considerably above that, you'd fully strip argon. And to get to the Schwinger limit, you have to get to 10 to the 29 watts per square centimeter, another 4 orders of magnitude. And that's actually displayed on this Maru chart. You can see the Schwinger limit up here and the most intense lasers we can make down here, okay? But there's a trick. There's a trick to getting higher intensity. And the trick is to co-locate, that is, in the same lab, this petawatt laser with a relativistic electron beam, just like the electron beam that I use for free electron laser research at SLAC. So here's a Google Earth view of my neighborhood, the SLAC linear accelerator. You can see it from outer space. And right down here is where we do our experiments, and it can produce electrons that have a Lorentz factor, a relativistic gamma of about 30,000. And the intensity in the center of the rest frame of the electrons that are counterpropagating with the petawatt laser goes up like 4 gamma squared. And that allows us to actually get from petawatt laser style intensities to intensities that are well above. So all we need to do is collide our laser with a relativistic electron beam, and we should see strong field physics coming directly out of the vacuum. And that's an experiment that is underway. Of course, with the laboratory shut down by the pandemic, things are delayed, but we expect to have our first chance to do that sometime later next year. Well, that gave me a chance to introduce the second revolution, the first being the colliding pulse, chirp pulse amplification. Chirp pulse amplification was truly a revolution in strong field physics. The second revolution is the brightest source of X-rays, the free electron laser. So here's a photograph of a laser that was the first X-ray, hard X-ray free electron laser in the world at SLAC, which has now been completely dismantled. That is 10 years old, we're on to version 2. So this is now a historical photograph of a laser that no longer exists, But let me show you some of the things that it did while it did exist, and then some of the things we're going to do with its replacement. The way a free electron laser works is it uses the relativistic electrons as the gain medium. Here is a cartoon of what happens to a bunch of relativistic electrons going through the laser. The laser consists of a lot of magnets periodically poled, north, south, north, south, north, south, like that. And when the electrons go through, they wiggle. Okay? When they wiggle, they radiate. And here's the thing. The electrons are going the speed of light. And so, or as close to the speed of light as makes no difference with a relativistic gamma of 30,000. But the light they make is also going the speed of light. But the electrons are not going in a straight line. They're wiggling. So the electrons have to travel further every wiggle than the light does. And they fall behind each other by exactly one wavelength of the resonant lasing condition for this laser. So this laser makes laser radiation with a wavelength that's given by that slippage. And that can be an X-ray wavelength. And so we can make X-rays in this way. There's absolutely no limitation to how bright it can be as long as you can keep the electrons coming. Now, we don't have mirrors to form an oscillating cavity, but we don't need them. We just need to unwrap an ordinary mirrored laser so that on every reflection, we just put another stage. And we have a very, very long, long laser, but it works. So what kind of radiation does it produce? Well, here's a picture of the light that comes out in one pulse. You see there are very short bursts. This is time. The bursts are considerably less than a single femtosecond. So they're a good time scale for us. The energy can be anywhere from a few hundred electron volts per photon up to 10 kilovolts or more per photon. So this turns out also to be the wavelength for studying atoms. And the peak brightness is about 1 billion times higher than any other source of X-ray radiation. The next brightest source are synchrotrons. So we are now learning, and have been for the last decade, learning how to use this for atomic physics. One of the kind of cool things that's recently been done by my colleagues Sichi Lee and James Cryan is just take one of these very, very short X-ray pulses and use it to produce an electron, ionize an atom, and then have the atom in the presence of a strong field. This is a circularly polarized field that can move the electron around just the same way as the strong fields that I've shown you in the earlier part of the talk. Then, depending on when the light pulse comes through and ionizes, the electron will get pulled in a different direction, and you should be able to see that oscillation as we slip the phase here, and that gives us an indication of how short these X-ray pulses are. So let's give it a try. Here is actually what things look like on the detector as I slowly move the phase shift between the attosecond X-rays and the laser field, and you can see the pattern of electrons moving around in a circle. Using this data, you can analyze this and find out that the X-ray pulses were around 300 femtoseconds long. And we've now used that as a stopwatch to measure processes in atoms. So for example, let's take a look at a very simple molecule. This is the NO molecule. When I hit it with an X-ray, either the oxygen or the nitrogen core electron can come out, the 1s electron. They have different binding energy because they have a different nuclear charge. And so they come out at different energies, and I'll see them in different places on my detector because of that. Here are the nitrogen electrons coming out. Here are the oxygen electrons coming out. This is data that is lined up so that you can see that there's a time delay between when the nitrogen electron come out and when the oxygen electron comes out, just because the oxygen electron has to climb out of a deeper potential well. So we're seeing very, very short timescales in these atoms right now. Okay, that was a fun demonstration of how short the pulses are and how you can do attosecond timing. But another really important feature of the X-ray laser is that the X-ray wavelengths are so short that we can actually use them to take images, real diffractive images of things that are just on the size scale of a molecule. And so here's how we do that. Again, this is done using the pump probe technique that I've been describing already. This particular demonstration has iodine stored in a vapor as the target, iodine molecule. So it's a diatomic molecule with 2 iodine atoms. We can excite it, and then with a time delay, can probe it with X-rays. The X-rays scatter from the excited iodine, hit the detector in different places, and I can measure the pattern of the hits as a function of the time delay. So I've showed the time delay here, and let's now run the data movie showing what happens. First of all, at negative 10 picoseconds, the X-rays come first. When the X-rays come first, all you see is the scattering pattern of the iodine. And it looks like this. That is, there are regions where there's more scattering, there's regions where there's less scattering, and the characteristic oscillation period here tells you something about the size of the iodine molecule. In fact, it's a measure of the iodine molecular size. Now, when the molecule gets excited, more stuff happens. Let's take a look. Now, I hope you can see this movie. You can see that as soon as we cross the threshold of the pump and probe overlapping, the whole pattern seems to collapse. And also, it gains a lot of interesting structure, transient structure along the way. So what's going on there? Well, that's diffractive imaging. And it's easy to understand for people who know a lot of optics, and I know that you do. So let's just look at optics on the X-ray scale. I have a plane wave of X-rays from my X-ray laser that will hit some molecule that has a bunch of atoms in it. And what happens at that point is the X-rays scatter elastically. So plane wave in, spherical wave out. Let's make the movie happen here. There's the spherical wave out. Now, actually, it's 2 spherical waves because there were 2 atoms here. And so the waves interfere with each other, and there are regions where you get maximum scattering right along here where the wave fronts line up. And if I excite the molecule, I can start to see those move. As the molecule wiggles, stretches, and compresses, the point of maximum overlap changes, and that's all we're seeing. So here it is happening with the movie. Now, in order to analyze this data, you can do a lot of things. Let me show you a very simple thing to do. Let's make a film strip of the amount of scattering as a function of radius here. Radius here is in momentum transfer space, which is called Q in X-ray scattering. So let's make that film strip. Here it is. This is time here, and this is Q, which is basically mapping onto the radial position here. And you can see all of the stuff that you can see in the movie, but now you can see it in a static film strip. You can see that before the excitation pulse comes along, you have a lot of scattering out here at around 2.7 inverse angstroms. As soon as the X-ray pulse excites the molecule, that drops down to around or a little under 2 inverse angstroms. And then also there's this sort of fallen curtain here stuff. All of that's real. In fact, if I look at the inverse Fourier transform or the cosine transform of this picture, that gives me the real picture, real space of the map of the separation between the iodine atoms as a function of time, which is really what a molecular movie is for a simple molecule like iodine. So here it is. We see that before excitation, the iodine is just sitting there at its equilibrium separation, which you can look up is right around 2.7 angstroms. So we seem to be calibrated well. It runs up to about 4 angstroms and starts to oscillate as soon as the excitation laser comes along. So that's a real space movie, and it's, as they say, de novo. That is, I didn't use theory of iodine to get this. I just looked with a well-calibrated X-ray source. So you can compare this, of course, to calculations. Typically, calculation for a molecule like iodine that's excited would show that from the ground state, I go up to an excited state, and then a wave packet sloshes back and forth. Here it is. Hope you can see that. But of course, since we've taken the data, let's turn this into a real space movie, like a motion picture. So just using this data, we can do that. Here's the movie. So all of the features of motion, including the initial bit of, a little bit of the molecular ensemble dissociates, but mostly it gets excited to a vibrational state. All of this could be seen. Now, we wanted to use this as a tool for strong field physics. So let's just do this kind of experiment, but turn up the field. So now we're going to try to do a strong field experiment where we use a focused 800 nanometer laser, our TISAF laser, as the pump, but it's the same probe and it's the same molecule. So everything is the same. Here's the movie. You see the movie looks quite different because actually everything changes when you change the excitation. You can see that in the level structure of the molecule. Now, to analyze this, I want to unpack this a little bit more carefully. You saw a lot of wiggling in this pattern. So let's look at one of the tiles, this one right here, and I'll just analyze how much light there is hitting that tile as a function of pump probe delay, and you can clearly see this wiggling. Now, if you're a spectroscopist and you see wiggling like this in a time scan, of course, you want to Fourier transform that guy, and so here's the Fourier transform. This wiggling is this says terahertz, but it's actually, there's a factor of 2 pi. It's teraradians per second. This is a 40 teraradian per second oscillation, and you also see a couple of other oscillations that are in this picture, but a little bit hard to see unless you do the Fourier transform. Okay? Now, we can do that for every point on the radius of this detector, and so we can make a film strip just like we did before. Here's the same film strip, only now for the strong field experiment, and time is going this way, radius or Q is going this way, and again you see regions where there's more scattering and less scattering. You can clearly see that 40 teraradian per second wiggle, okay? But just as I did for the single tile, now let's Fourier transform along the time delay axis and see what this picture looks like. And you see the pattern changes enormously. Here's the real part of the Fourier transform. So now this is frequency of oscillation versus Q, and here's the imaginary part. And a number of features start to show up. Let's analyze these features. Actually, the easiest thing for me to do quickly in a colloquium is to combine these two into the power spectrum, which I've done here. Here's the power spectrum just by squaring the real and imaginary parts added together. And you can see that there are these straight lines and there are these horizontal lines. So what are they? Well, the horizontal lines first, those are lines of very constant oscillation frequency. Those are the vibrations that are excited by the strong field. And the brightest one is the impulsive stimulated Raman scattering oscillation, where a photon is absorbed and one is emitted, leaving me in an excited vibrational state of the molecule. That is by far the strongest thing going on. You can measure in the data the oscillation frequency and compare it to the NIST database, and it all works out quite well. There are also these sloping lines. These sloping lines have to do with dissociation, nonlinear dissociation in this case, where two photons are excited and we can either decay to the ground state of two iodine atoms or to the first excited state, where one of the iodine atoms is in its first excited state, the fine structure split state. Okay, well, lots of fun, right? And you can see that I'm just skimming the surface of the physics that can be derived from these kinds of observations. But as I said, that laser's been dismantled now. Why? Well, because a new laser has appeared in its place. The new laser is called LCLS-2, not very imaginative naming a new laser, And the difference now is that this laser is a superconducting linear accelerator for the electrons, which can run at a much higher rate. All of those experiments I showed you were running at 120 hertz. Now we can run at 100 kilohertz or even up to a megahertz. And also, we took advantage of the shutdown time to upgrade the undulators as well. So LCLS2 will be quite an advance. It'll actually have 1,000 times, again, higher average brightness than LCLS1, the laser that was just decommissioned. And there's lots of new opportunities because of that. In fact, if you're interested, if you think you might want to participate in some of these science adventures, take a look at new science opportunities enabled by LCLS2, which is a Slack publication online, or the Department of Energy in the United States has also had its own workshops talking about opportunities. So that brings me to the end. Here's just a brief summary. What I hope I've been able to show you in a brief time here is that ultrafast science is the science of exploring motion that's happening down at the quantum scale. The way we do this is with coherent excitation and coherent readout with ultra-short pairs of pulses. There's a straight connection to this ultrafast science all the way back to the original Rabi atomic beam as improved by Ramsey. Ramsey was the first person to say, actually, if you excite a system twice, you get much better information about it, and that's just what we're doing still. And new technologies are still coming along to expand the laser wavelengths and the power and expanding areas of science impact. Now we can make these lasers from terahertz all the way out to hard X-rays. The hard X-ray lasers themselves are quite interesting, important, unique tools. They're getting built now in different parts of the world, not just in California. They let us view the actions of quantum processes down at the level of a chemical bond. So here's my group at the present time. What I showed you was a range of research that covers a decade, so there's more people involved. But I really owe it to my group. You can see that it has a lot of members in it, partly because we're closely tied to the Pulse Institute. So some of these individuals, like James Cryan and Adi Natan, are actually colleagues of mine in Pulse. We run these research in a collaborative way. We have lots of other postdocs and a whole raft of students, of course, and a fairly robust new crop coming in every year as well. So with that, I'd like to thank everybody for your attention, and I'd be happy to answer any questions. Thanks. And also, I'll stop sharing so I can maybe begin to see some people.
So thank you, Phil, for this very nice talk. So we do have questions here, so I'll pass them on to you, so if that's okay. But thank you again for the very nice talk and very exciting physics being discussed. So I'll just start with one of curiosity of mine first, then I'll go through the YouTube questions. So the question I have is, when you show this finger limit, so you want basically to collide your lasers with electrons, right? So my question is, how hard is actually, how difficult is to do this based on a cross section? Do you have any problems with the intensity of the beam? Because probably, I guess that's one issue, right? So could you comment on that?
It certainly is. As most of you know, the interaction between light and an electron is governed by the Thomson cross-section, which is a lot smaller than an atomic cross-section, 10 to the minus 24. However, there's a lot of photons in a petawatt laser, and there's a lot of electrons in one of these ultra-relativistic electron bunches. In fact, we tend to measure these things in nanocoulombs. So there's on the order of 10 to the 10 electrons. And of course, there are joules of photons. 10 to the 19. And the focus is tight enough that the answer is that the interaction is actually quite strong. In fact, the expectation is that hundreds of electron-positron pairs can be made in a head-on collision. And what's even more interesting, of course, is that there's different kinds of physics involved. So the one that we're really interested in, because it's this true Schwinger physics, is we want to look at a backscattered photon, backscattered from the relativistic electron bunch. That backscattered photon, of course, will be a gamma ray, because in the lab frame, it's really upshifted by the Doppler shift. And then that gamma ray interacting back with the laser beam itself, because that's a region of space where there's no electrons anymore. It's just pure vacuum. And that's where the electron-positron pairs come out because of the Schwinger process. But in addition, you have the electrons are also present, and they can also assist. And the electron-assisted particle production is also going to be quite prodigious. So we don't expect seeing a signal will be a problem. We expect separating the different components of the signal really to be the challenge.
Okay, thanks for the nice explanation. So I'll just pass a question now by Jonathan. So actually he has two questions. First, he thanks you for the nice talk. And then he asks, do high harmonic spectroscopy and ATI spectroscopy provide similar information, or they are complementary?
Well, they're certainly both similar and complementary. That is, the interesting thing about the high harmonics is that they involve recombination of electrons that have been away for a while, on the order of half a cycle of the laser field, and then come back. And so they have a property that people in the field called auto-chirp, meaning that the energy of the harmonic is encoded to the amount of time the electron was away. And so that means by looking across the harmonic spectrum, I'm actually looking across time with the more distant, it depends on which trajectories, but with the more distant electrons, or the ones that come out back and produce the higher energies, actually producing that at a different time than the ones that produce the lower energies. And I can see, I can make a movie just by looking at that spectrum. I can interpret it as a movie of what was going on in the cation, the singly charged ion, as the electron was returning. So people have used it for that. You can't get that information so easily out of the ATI by itself. But the ATI gives you different kind of information. It gives you information about the neutral when the ionization was happening. So you get to actually, it's like a microscope on the tunnel ionization process. And so we've been using it to understand that. And then the other thing that you get from the above threshold ionization is, of course, the ATI spectrum is extremely complex compared to the photon spectrum from high harmonics, because there's angular information. You know, you get to see electrons, trajectories that go in all different directions. And so that's another really powerful thing that we make use of. That's a kind of, we can use a kind of a holographic principle to think of that very beautiful ATI spectrum as a hologram of the atom as viewed by the electrons that it was emitting. A really good analogy is a field ion microscope. Many people know probably that a field ion microscope is a way of doing atomic scale investigations of the microscope tip, because as the electrons come off, they come off in a pattern that tells you what the crystalline structure of the tip was. So it's the same thing with the ATI and these ATI spectra and these molecules.
So thank you so much. So there is another one from him. So regarding the recent demonstration of the free electron laser atom-second pulses, what is the method to obtain atom-second synchronization for atom-second optical pump, X-ray probe, and how stable is it?
Yeah, it's a really, really good question. That's okay. So there's a couple of answers because there's more than one way, because people are thinking of a number of ways of doing this. The most direct way is to reference you back to the actual movie that I showed. That showed, I showed that as we changed the time between between the oscillating strong field that was circularly polarized and the attosecond pulse that was ionizing an atom, that the photoionization electrons would get streaked in different directions, okay? So that's one way of measuring the time. So if you have a pair of attosecond pulses and you have the opportunity to send them through a device like that, they will each produce their own electron signature that's streaked at a different direction because of the difference in time between those two pulses. So it's sort of the flip side of being able to measure that the oxygen electron and the nitrogen electron come out at different times when they're hit by the same attosecond pulse. I can also show that two attosecond pulses will be streaked in a different direction by that same kind of streak camera. So that's actually the most direct thing you can do. Now, it isn't always possible to have that as a kind of a downstream ancillary diagnostic experiment so that you know what the pulse separation is and then you can do physics with that pulse separation. Sometimes you have to figure it out in less direct ways. And so one of the interesting indirect ways that we can use is to look at this is a really interesting one because you can't do this in an ordinary laser. We can look at the spent electrons from the laser. So, it's a relativistic electron beam, right? As it goes through the undulator, it makes laser light. If we arrange it correctly, we can get it to make two X-ray laser pulses. And so the electron bunch then is making an attosecond pulse in one place and an attosecond pulse in another place in the bunch. So if we can go then analyze what parts of that bunch had their energy depleted because it went into making an X-ray, that's another way. It's indirect, but it's another way of measuring the separation between the pulses. And what's really cool is that it works because the X-ray laser is efficient enough that it takes enough energy out of the relativistic electron bunch to see the change in the energy. You just send the electron bunch through a spectrometer, and you see that here's a little parts of the bunch have a different energy. So there's that indirect way as well.
So thanks for the...
Those aren't the only two ways, by the way, but I'll stop there.
No, thanks. That's really enlightening. Thanks. So there's now a question from Vanderlei. So he asks if are there any proposals of free electron laser for medical and therapeutic applications?
Well, sure. In fact, our lab wasn't completely shut down by the pandemic because we kept part of it operating specifically so that we could do research on that was related to COVID-19. So what kind of research is that? That's mostly in the area of molecular structure determination. We can, I do molecular physics. So I use these hard X-rays. I go through an ensemble of molecules. The molecules are really small. There's a whole ensemble of them. But there's another way of doing physics with this machine, and that is use the same X-rays, but instead of an ensemble of some gas phase molecule, you put a single macro molecule in there, a single virus or a single nano cluster of biological materials. And the X-rays are focused into that. There's only one of those nanoparticles in there or one of those viruses in there. And all of the X-rays scatter, and in a single shot, you get an image, okay? Of course, they get more than one shot. They then can collect together the images from millions of those shots. And there's a lot of sophisticated ways to analyze that data to kind of get them to all overlap with each other to get structure determination. So not only have they been able to measure the structure of things that you can't crystallize by using this method with the free electron laser, they've also been able to look at motion because you can get some chemical reaction to start happening. I'm not talking ultrafast here. It could take a second, right? But you can prepare your sample of whatever it is, some biological stuff. You can prepare it by exciting it or mixing it in advance, wait a certain amount of time, and then look at it. And so using that as a function of that time delay, you can measure how reactions are happening in biological materials. So both of these technologies have been in use.
So thanks. There's now a question from Lucas. He asks, well, first he asks, well, most of if these methods are destructive or not, and if you could prepare an ensemble of molecules to study their dynamics in a sense that they are as identical as possible.
You mean how can we make the ensemble? Was this how can we make the ensemble identical as possible?
Exactly. And so if you do like you want to study identical particles or identical dynamics.
Right. So there's a lot of tricks. Most of them made with cool laser stuff. One of the things that we've perfected in my lab is impulsive alignment or even orientation, where you use a very special train of pulses with their polarization fixed in a special way, and they come in early and they excite rotational modes of the molecules in the gas, but they excite them coherently, of course. And then you wait just the right amount of time until those rotational wave packets have all phased correctly, and you can actually make an aligned ensemble that way. You can actually do even better than just an aligned ensemble. You can get ensembles that where the degree of alignment and the orientation of the molecule is something that you can control. So these are ways of varying knobs you can turn in your experiment to understand what's going on with the external degrees of freedom, the rotational degrees of freedom of your system. So that's certainly one of the methods we use. Another method, which is not one that I've used, but other people do this, is a substrate. You can use a substrate. So the idea there is, we prepare things in a gas, but you can actually also look at materials on surfaces, particularly on very thin surfaces. So, for example, two-dimensional surfaces like graphene or other kinds of two-dimensional surfaces are ways of preparing a sample, or even just a thin amorphous polymer material. And that's another way of knowing what the orientation is. And then the third way is use the rules for photoexcitation. So for example, in a typical molecule that isn't spherical like an atom, when you excite it by light, only the subset of the molecules that have a particular orientation so that their dipole moment is aligned with the polarization of your light will be excited. And the ones that have their dipole moment in some other direction will be excited much less or not at all. So even though your ground state sample is completely isotropic, the excited components of your sample are highly anisotropic. And actually, I didn't mention it because I was just doing an overview, but all of the data I showed you for our X-ray scattering experiments have that feature of what we call geometric excitation, just because of the molecules that were in the right alignment happen to be the ones that could be excited by the laser.
So thanks for the explanation. Now we have let's say a question related to lasers, but not directed to your talk. So our colleague of ours, Victor, he asks if you can please comment on the use of laser interferometry in the discovery of the gravitational waves at LIGO. And I mean, what are the challenges in this field, and what can you do with this kind of technology in the field? I mean, to study gravitational waves or something as subtle as this.
Well, LIGO is a wonderful laser experiment, And, with all of our excitement about X-ray lasers, LIGO has even more excitement associated with it. And, you could say that the lasers are quite different. In some ways they are, but they have a couple of things in common. And so there is some common technology there. One is that the power is very high inside the LIGO cavity. It needs to be. And also the coherence is very high. And we also take advantage of both of those properties. And in fact, both of those properties come directly from the opportunity to use solid state lasers, which have been very, very well developed over the last few decades. So, what are the new things they're doing with LIGO? Of course, is they're actually using squeezing methods, basically using squeezed light to get even closer to or beyond the standard quantum limit in the sensitivity for LIGO. That's really just a wonderful feature. We're very, very far from being able to do similar things like that with our pulse lasers, but we certainly appreciate the technology that's involved and a lot of the common understanding that's needed to do it.
So thanks a lot for the answer. So I see no further questions here at the chat. So I'd like to thank you once more for your kind talk, for accepting our invitation, for the nice talk, and for answering all the questions. It was really a pleasure.
Eric, I'd like to thank you for the invitation. Really, this was a great privilege, and as you and Vanderlei have said several times, I really do look forward to actually being able to come to Brazil sometime in the near future when all of this is behind us.
So I really hope you can make it. So, okay, we got just one last question, so if you do not mind. So the last one from Jonathan. And he's asking how strong electron correlation effect like Cooper pair formation can be studied with ultrafast X-ray spectroscopy. So he's trying to...
How strongly correlated systems?
Yeah, like for instance, he specifically asks for Cooper pair formation in superconductors can be studied by ultrafast X-ray spectroscopy.
Right, and as you probably know, there are a group of people who are in my field in ultrafast physics who have been studying how ultrafast laser excitations give you the opportunity to look at things like transient superconductivity, that is, correlations that are present but not present for very long. That are induced by the laser and can be measured using these experiments, and I think that's a fascinating field. Now, the interesting thing about strongly correlated systems is that they're quite often tied to technological needs. That is, it's wonderful fundamental physics, but also let's face it, people would love the idea of being able to make a room temperature superconductor, for example.
True.
And as far as I know, these methods are thought of as one avenue that might eventually get us there. That is, get us the opportunity to see what's the right path to take to find higher TC and more stable eventually superconductivity. So it's not my field. I follow it with great interest, particularly when it starts to overlap ultrafast physics, and I know a lot of the people who are involved in that aspect of it. But that's basically that's what I know.
Thanks once again. It was really a pleasure. So I guess I'll just finish the broadcast here. So again, I'm just thank you so